Today is June 4th, 2022. It is a Saturday, and today in my gummy bear project, I'm up to the inference analysis section, the test of hypotheses. So what I'm going to be doing is performing a hypotheses test on my data. Last time I was here, which I think was video 3, log 3 of this project, I did a confidence interval, and I just walked you through my thought process, and I also showed the me actually doing it, both in Python and in real life. So this is what it looks like, and so I'll be doing the same thing for the hypotheses. And so I'm going to turn on my whiteboard here. So again, if I'm doing a hypotheses test, I will be using Phantom. P stands for parameter, H stands for hypotheses, A stands for assumptions, N for the name of procedure, T for the test, O for obtain p-value, and M for make conclusion. All right, so let's start with, let's see, hold on, my button isn't showing, not my button, my mouse. Let me close this real quick and open it again. All right. Oh, by the way, today is day 318, I think. Let me check real quick. Today is day 3. Oh, no, wait. Oh, today's day 321. Wait, is it? Yeah, Saturday. Yeah, day 321 of data science. At this point, I don't even keep track. Or remember, I just copy and paste and then change the number. Okay, so hypotheses, Phantom. So we'll start with the P. So again, P stands for parameter. So the parameter that we're trying to estimate, right, is mu diff, right? So the mean difference. And this is the true mean difference in distance traveled by gummy bears. Oops. So the parameter is basically, the idea of the test is that, you have a population, right? But it's unrealistic for us to get every single subject in that population. And so because of that, we only take like a sample of that population. And so with that sample, we can estimate the true values or the true parameters from the population, right? But we're using basically statistics to estimate parameters. So again, here in a sample, you have statistics that we can use to estimate parameters, right? From the true population. So they're basically the same thing, except that, the population has the true values, right? But statistics are just things that are the same thing as parameters, but like it's an estimate of those parameters. So they're close, but there's a chance that they're not exactly right. And so with hypotheses tests, we can basically have hypotheses or like predict things and then try to see if they're right or not using data. So the parameter that we're trying to estimate, right, is mu difference. So this is the true mean difference in distance traveled by gummy bears. We already have the mean difference. The mean difference is negative 0.9 something. Let me just pull it up really quickly. I calculated it 2 days ago for the confidence interval. Hold on. 319. See, the mean difference is negative 0.93133, repeating whatever. So that's the mean difference, right? But is it what we're trying to do is find the true mean difference, because that mean difference, we calculated it from a sample, right? So again, we have the population of gummy bears, right? And we have a lot of gummy bears. But what we're doing is we're basically taking a sample of those gummy bears, and we're finding the mu difference, right, between the two between the two treatments. And that mu difference is actually the statistic And essentially, if we're talking like technical, it would be X bar difference because this is the statistic for mean, and then this is the parameter for mean. So yeah, so this mean difference is essentially what we found is negative 0.931, whatever it was. That is an estimate of the true mean difference, right, in distance traveled by gummy bears. So that's the idea here. I'm trying to find I'm trying to estimate the true mean difference. That's why we say the true mean difference, because that's your parameter from a population. Okay, moving on. So we have the hypotheses. So we have the original hypotheses and the alternative hypotheses. So since we're working with mean, we start with this mu. So we're going to say that mu is equal to 0, which is the original hypothesis. And then my alternative hypothesis is that mu, I'm sorry, not mu, it's mu diff equal to 0. My alternative hypothesis is that the mu difference is not 0. So this is saying that there is no difference. This is saying there is a difference. All right, so we have hypotheses. You know, when you have an experiment, you make hypotheses or predictions, etc. So the original hypothesis is that there is no difference, and we're trying to find evidence for the fact that there is not a difference. And so the question here would be, is there convincing evidence that the true mean difference in distance traveled by gummy bears, that there is a true mean difference in distance traveled by gummy bears, or is there convincing evidence that there's not, etc., whatever. Anyway, that's our hypotheses, and then we have assumptions. Assumptions, you can think of them as conditions that you have to check um, before conducting a hypothesis test. And even if the conditions don't meet out, in AP Stats at least, you still have to continue on with the hypothesis test and just say proceed with caution, even though the conditions are not met. But in this case, let's see. So for A, not for A, number 1, the first condition is that the samples have to be random. And so in my experiment, again, I did conduct an experiment, and they were random samples of gummy bears, and it was 30. It was an SRS, a simple random sample of 30 gummy bears, right? Because we got 30 random gummy bears from a bag, and so it was a simple random sample of 30 gummy bears. So that condition is checked, okay? Second, we have the 10% rule that checks for independence. So independence means that, one outcome wasn't dependent on another outcome. So they were each independent. So for example, the one gummy bear being picked um, wasn't dependent on another gummy bear being picked. But if you actually think about it, it was, because if you have a gummy bear bag and you take one out, then obviously that's not going to be picked again. But there is a condition which states that the sample size has to be less than or equal to or 10% of the population, or 0.10 n. So if it meets that condition, then they are independent. So in this case, we had 30, which was a sample size, and it's less than or equal to 10% of the population size n, but we don't have that. So because we don't have that, we just say all gummy bears. And at least College Board likes to say that. And then what we say is that this is reasonably true, because it is reasonably true. Like 30 is definitely less than 10% of all gummy bears in the world. So like, yeah. So reasonably true, and then we move on. Then the last one is normality. So we have to check for the normality condition. And this condition is when n is greater than or equal to 30. So we already know that n is 30, right? Because we had 30 gummy bears, and it is greater than or equal to 30. Okay? Now, those conditions are met, and then we can say we can proceed with the hypothesis test. So then we have n. N is the name of the procedure. So this is a one sample t int, stands for interval. I'm sorry, not interval. We're not doing confidence interval. T-test. Excuse me. One sample t-test for mu diff, or you can write it as mean difference, right? Because you're performing a one sample t-test for a mean difference. Because again, we only have one sample, because we only took 30, right? One bag and we took 30, so that was one sample. Um, and we're doing a t-test because we're working with mean. Again, when we're working with proportions, we use z. When we're working with means, we use t. And the reason we use t is because, let me see if I can remember. It has to do with standard deviation or something. I think the equation has, let me see, it's actually in my notes. The equation for z requires, I think, the population standard deviation, and we don't have that. I'm not sure. I have it in my notes. One second. Statistics. Let's see if I can find it. It's where I started doing t-tests. I'm not sure when that was. Let me see. Was this a t-test? Yeah, this was a t-test. Oh my God, would you look at that? It's a mu difference. Wow, that's cool. See? Oh, I love this. Memories. So yeah, this is mu diff. Actually, you know what? I'm actually gonna screenshot this and to go back to it just to give you like, oh look, I even did a visualization of it. Oh, that's so cute. Okay, great. I'm gonna take a screenshot of this. What a coincidence, really. How do I land on an exact similar problem? All right, did I take a screenshot? This thing literally just freezed out. Like what? Let's see. I'm just gonna save that real quick. I'm gonna open this. Oops. I'm gonna save that right there. So what page was that? 77? Okay, so it should be like right above. Like I remember the introduction, it was a PDF, and I had written it down. Should be somewhere here. No. Let me see. I know I wrote it somewhere. Is it this one? Yeah, here we go. See? I love writing notes. Okay, so here's the reason we use T. So T, oh wait. No, hold on. No, yeah. So essentially, a t-test is when we use T-star. So T-star basically is used to estimate the mean. Why T-star and not Z-star? Because to find the mean for a, oh see, I was right. Okay, great. Because to find the mean for a population, we need the standard deviation population, which is incredibly hard to find. So we use an estimation of the population standard deviation. Okay, hopefully that makes sense. What difference does it make when using T-star? So if n decreases, if the sample size decreases the distribution, if the sample size decreases, the distribution gets shorter and wider, while using Z star, if n decreases, the distribution does not change. Okay, but let's go back to this. Let me try to remember here. So T star is used to estimate mean instead of Z star because to find the mean for a population, we need the standard deviation for the population, sigma, which is incredibly hard to find. So we use the estimation of the population standard deviation, which is what T star has, because Z star doesn't have. Oh yeah, I was just gonna look at I was gonna try to look at the equations and they're right here. See, this is why we write notes and we save them. Okay, so T star is S over square root of n. Oh, so it's the same thing. Hold on. Let me think. Z star S over the square root of n. Okay, but we don't know the sample size because I think what it is that instead of, I think I messed up and put lowercase n, I think it's capital N. right? Because the reason why we use Tstar is because it becomes kind of a statistic. Huh, interesting. Let's do some research on this. Why use T star for mean and not Z star? The T distribution is more probably to observation of tails and then the center number distribution. No. How to know when to use T value or Z value? For hypotheses tested. Well, you don't do a t-test. Hold on. Oh, wow. Oh, okay. So the population standard deviation isn't known because sometimes they do give it to you, but it's incredibly hard to find. So if it's not known, then you use t-test. But why does it have to do with the equation? I know because it's needed, but I want to look at the equation and like my equations look off. I know they're right, but like maybe I messed up and wrote lowercase n versus capital N. Trying to think. T-test equation AP stat. Because sometimes if you just search it up, it gives you a weird thing. I need the AP stat version. It maybe make it look. There we go. See, but that's weird though. Isn't that Z? See, look at that. Z is equal to x minus mu over sigma. X minus mu over sigma. And then T star. Oh, why did I forget about that? Let me know. I just realized. Okay, yeah, so it makes sense. Z is equal to x minus mu over sigma, but because in our mean problems we don't have sigma, it replaces it with x minus mu over the s over the square root of n. That makes much more sense. Yes, yes, yes. Right, so here we go. Here it's s, right? The standard deviation of the difference over the square root of that. Now, only thing is, it's this one, right? Yeah. Because making it capital doesn't make sense. So I'm going to save this, and I'll put it in my gummy bear project. If you wonder why I have a picture of Olaf, it's because I was trying to 3D model him yesterday. Did not work out. Okay, gummy bear project. Put that in there. Why can't I ever save it as an image? Can I just save it as a JPEG? Whatever. And then, where were we? I had Z, which was this one, right? Sigma? It's not sigma over the square root of n, though. That's T. Huh. Ooh, this one's prettier. Let me save this one. Let me call it T. What about the Z test? I don't think, wait, I don't even remember. I just had it, it's right there, yeah. Here we go, this one's prettier. Alright, save as. Actually, hold up, this one's prettier. Actually, no, this one is prettier. Yes, okay, save as. We're gonna call this Z test. Alright, so to kind of summarize, because I'm all over the place right now. So if I go back to my notes, we use T star because to find the mean for a population, we need to have the standard deviation population, right, for Z. And so Z doesn't have, wait, Z has a standard deviation population, but sometimes we're not given that. So then we use T, which has S, which is the statistic. What was I gonna say? Yeah, the statistic instead of the parameter. So I believe. Maybe I'm explaining that really wrong. I'm trying to think. Um, Hold on. Can I screen capture? What is going? Oh my god. Oh my god, wait, I can screen cap. Oh, but I don't want to lose this. Let me save it. Oh, where am I saving this? Okay, Gummy Bear project. Whatever. All right. Screen capture. Just take everything. All right. So, hopefully my computer doesn't crash. Okay. So, essentially, the idea is that we usually start with, well, we always essentially use Z. Oh no, it's gonna crash. Okay, let me save this. Whoops. Okay. Z versus T. All right, and then let me open this in the whiteboard in a new one because I'm gonna save this later. All right, 1 second. All right, so let me go here. Images. What the? Where's my stuff? Oh, Gummy Bear. Where is it? Over here. All right. Lock it in. All right. So the idea was that I'm trying to explain basically why am I using Tstar instead of Z. Because Z, right? Let me use another color. Every time I try to say something comes out. Okay. So you get Z by doing your statistic minus your parameter, right? It's the same thing, except that, one is from a sample, one is from a population, S sample, P population. Okay. And then you divide it by the standard deviation of the population, right? And, we are given X bar, which is the mean that we just find. We usually are given that. The population mean, let me give 1 second. What did this guy say? Or what did I say? We need the population, standard deviation, which is incredibly hard to find, but that doesn't make sense because what did I do? Hold on. Z star, the margin of error, T star, S, Z star, sigma. Okay, I think the whole idea is that we don't have a standard deviation from the population, and so because we don't have those parameters, we have to use T, which is basically an estimate of all of those parameters together. But then my question is, why is mu here? Because usually mu comes from our hypotheses, right? So if I said, okay, mu diff is equal to 0, and then my alternative hypotheses is that mu difference is not equal to 0, then mu, right, would be your 0. That's where it comes from. Oh, right, because, okay, let's think. Hold on. Right, because this is what we're testing. So we're substituting this. We're saying, oh, okay. And then we use the p-value to see if it's significant. So that's why this doesn't matter, because I know both of these are, well, so from what my understanding, okay, we need the population standard deviation when we use Z, and we don't have that, right? When usually. So because of that, we use t instead, which has a statistic for the standard deviation s, and we can get that by taking the standard deviation from our sample and plugging it in there, which I believe in our case it's 48 point something. And then n would be 30, x bar would be whatever our mu difference is, I believe, which is negative 0.9 something blah blah blah, and then mu, right, which in this case would be our mu difference, would be 0. Right? I think that's what we're gonna do. Right? I think. Am I doubting myself? Probably. Okay. Um, yeah, so T stat, not T stat, T stat, T versus Z. I just know the really basic definition. Z is for proportions, and T is for means. Because for proportions, isn't it X over N? Huh. Oh my God. Okay. Uh, Let me think. Why use T versus Z? I mean, I understand that sometimes the population standard deviation is not given, but then why? But this is also a parameter. But this is also not given. We are the ones who put a guess basically because we're trying to find like I don't think it's real. Is any of this real? I'm just questioning myself now. Like, what is this? Like, who invented this? So I think because we're hypothesis testing, we're testing. Oh, obviously, we're testing a hypothesis. So we're testing a hypothesis value, even though that might not be true. Oh, that's why we use the p-value, right? I made this realization earlier. I don't know why I'm saying oh. Well, that's why we use the p-value to see if it's convincing, statistically significant, right? Okay. Okay. So even though I say, oh, we're not using z because we don't know the population standard deviation, and then you might question, okay, but we don't know mu, which is like the true mean, but we're testing a certain value for mu to see if it's actually true, so we can replace that. So this is fine, but we don't know this, and so that's why we use t, which has a statistic standard deviation, which we can get from the sample. Okay, that makes sense. Okay, so now that that's done and covered, let's go back to the actual work. Okay, so let me go back to my whiteboard without figuring things out and taking 20 minutes to do so. All right, what time is it? I can't even see. Okay. All right. So we figured why. We do that now. I'm gonna use an eraser. What is going on? Why can't I see my mouse? This always happens. I'm gonna get out of here and open this again. Did I just close my tab? Yes, I did. Okay, that's the point. I thought I closed this one. Oops. All right. Okay, let's think. Where were we? The second one. Oh, it's 507. Why does this keep don't show this again? All right, so one sample t-test for mean. So again, we already went over why it's a t-test and not a z-test. Also, essentially, the whole thing is you just want to remember, I just wrote it down, that proportions are for z, mu means, right, are for t, right? So that's it. That's the idea. Okay, so what was I doing again? So we got that done. And then t is our test statistic. Why is it like that? Okay, t is our test statistic. So this is where we get our equation. Whoops. So t is equal to mu. Interesting. I know down here is xx over the square root of n. But then here we have mu difference minus x bar. Now just give me 1 second because I'm trying to double check something here. This is for matched pairs, right? It's the average difference we're trying to find. Yeah, that's what we're trying to find here. So, what was I doing again? Okay, so we just plug in the values, man. So I know square root of 30 because that is equal to 30. X bar, oh, this is why it wasn't making sense to me. I forgot to add this. Okay, much more sense. So X difference, the statistic that we found from our sample was negative 0.9. So I failed in my code when I called it mu diff, right? Because it's not necessarily mu diff, right? What I calculated was x bar diff, right? The mean average difference from a sample, right? That's why we see it here. See why the heck? Sorry, come on. So I'm gonna go back to my code and fix that. So it wasn't mu diff, that is the parameter. What I found was x diff, x bar diff. Okay, and then this is the diff standard deviation. Right, and then this is mu diff over here. And so this is mean diff. Let's change that. It's still gonna be the same thing. Well, I have to run it from the beginning, but yep. I think that's all good. All right, let me reload that. So let me load all of that. So what did I do? Oh, I have to upload it again. Great. Okay, let's go to Gummy Bear Project. Oh, wait. I think I forgot to add it to my Gummy Bear thing. Was it this one? Can we also move it, please, to Gummy Bear? Here. Gummy Bear, where is it? Copy of data treatment too. All right, now let's close this and then run everything. And it's still gonna give me the same thing. See? Same thing. Whoops, I meant Ttest. Ttest. Let's do that one more time. Forgot those two variables. Right? Should give me the same thing. Okay, I literally just changed the name of udiff to xdiff because what we found was a statistic from a sample, not from the population. What we're trying to estimate, right, is the mu diff, which is from the true average a true average difference in distance traveled by the gummy bears, which is from the population, right? Because it's the true one. This x diff, right, x bar, the mean difference, is just an estimate from a sample, from our sample data, because, right? Yeah. Okay, anyway, so that's done. All right, oh yeah, I had this for later. So, what was I gonna say? What was my point here? Oh yeah, I was gonna show. Oh yeah, well yeah, I did figure that out. So I was actually gonna get the statistics. Why am I like this? Okay. Oh yes, I was sick. I'm still sick, but I'm feeling better. Okay, where are we? Where is my stuff? I should be more organized. Okay. Where is it? Okay, xdiff was this, right? So I'm just gonna copy this. Actually, you know, I'm not gonna copy it. I'm just going to write it as it is. So let me go here. So it was negative 0.93 13 minus 0. And our standard deviation was 48.8605. Now, here's the thing. I'm writing it with 4 decimal places because that's usually how they want it in College Board, but when I'm actually performing my calculations, I'm literally gonna put 0 point, negative 0.9, 13, 33, 33, 33, whatever, or 31, 33, whatever, in the calculator. And I'm also gonna show you how to do this in Python. That's the whole point of data science here. I have a function written for it though, somewhere in days in the other one, the one before this. I think days, what was it? Days 200 and 300. Yeah, so I have a function somewhere. I'll just have to find it. Or I could just write it myself. We'll write it. I'll show you how to write it. I'll walk you through it. Okay. So yeah, and then the mu diff, right? We get it from our hypotheses. So whatever these values are, is whatever that value is. By the way, these values are always the same. Little hack there, just in case you forget. Let's see, because that's what we're estimating. Okay, and then we just perform the calculations. We use our calculator. Where is my phone? Okay, I have to find my phone. Hold on. No, seriously, like, where's my phone? What? Oh my god. My palette just fell. Great. Oh, what? All right, so, oh, there's my phone. It's my, oh, great. So let me pull out my calculator. Okay, so negative 0. Actually, why do I need my phone? I could have just done this here in Python. Oh, God bless me. Okay. So Python also is literally, it works with numbers. So we treat it as a calculator. So we'll just do negative. You know what? I'll do, let me think. Let me start from the beginning. So I'll import pandas as PD because I don't want to manually write the thing, and I'll just do data. What the? Okay, data is equal to PD dot read CSV, and I'll just go to files and then right click and copy path and then just put that there. So this is what my data looks like, right? The first 5 rows. Okay, and then what was I gonna do again? Oh yeah, so I'll just do the skeleton of it, right? So T is going to be equal to data. Oh, this is the wrong one. Oh, it's not the wrong one. I just forgot to do Jesus Christ. You know what? Okay, hold on one second. So data dot differences. I'm just gonna call it diff. I don't have time for this. Data dot diff is equal to data treatment. Really? Treatment 1 minus data treatment 2. Okay, run that, and there should be another column called diff. And let me wow, I cannot speak. Oh my god. Let me make sure that is the same. 29, negative 31. Okay, what do we have here? 29, negative 31. Okay, perfect. Okay, it's the same. So T is equal to X, the average difference for the statistic, which is just diff, diff, oh, it's capital D, dot mean, right? Okay. Minus the mu difference, which is just 0. And then all of that, so I'm going to put that in parentheses, and I will divide that by the standard deviation of the difference, which is just data diff, right? So that column, so the differences dot std. And it's because it's a sample, DDOF is equal to 1, because when it's a sample, here we go again with the equations. Okay, so when you're calculating standard deviation for a sample, you have, in the equation, let me pull it up. There is n minus 1 at the bottom if it's for a sample, but if it's for sigma, which is from a population, it's just a capital N. Let me look at the equation for sample. Oh, here it is. Whoops. You see n minus, what the heck? What's going on? n minus 1 is at the bottom when it's from a sample. But if it's from sigma, it's just going to be capital N. Minus 1 is the degree of freedom, so it basically gives some freedom for some bias, like because there's always going to be bias in samples, and so you want to account for that, and so that's why they do like minus 1 from the sample size, just in case. So but DDoF is actually automatically set to 1 in Python, so you could just run it or delete it, doesn't matter, but I always like to specify, but I'll delete it for simplicity's sake. But if you're using NumPy, DDoF is actually set to 0, so I feel like NumPy is best for, so you work better for popular, okay, whatever. Anyway, that's what it is. That's what it is. DDoF is equal to 1, but it's automatically there. So, what was I gonna say again? I forgot. Oh, you divide by NDiff. So let me do something real quick. So I'll import math just so I can use the square root function, and then I'll also. Are you kidding? N is going to be equal to the length, right, of data diff. And so what I'll do is I'll divide by math dot square root n, and I think that's it. I'll put all of this in its own parenthesis also, so that they each get calculated individually. And then I'll just do t so that it prints t, run that, and then I get my tstat. Now, just to show you, n is literally 30, so it's going to give you the same answer, right? Yeah. Okay, so basically this just gave me the length of the differences, right? And you can see that, let's say I do 31, not 21, 31. You'll see that they only have oh yeah, 30. Oh, I got so scared. I was like, why is there only 29? It's because Python starts counting by 0 with 0. But you could also see the shape here. If you do data.shape, you can see the amount of rows it has and the amount of columns. Whoops. Hurry up. So 30 rows and 3 columns. So you could see that also by doing that. But yeah, that's the idea. So this is our basically our tstat, and we round to 4 decimal places, by the way. So t and then 4, we use the round function, round 4 decimal places, and so our tstat is actually negative 0.1044. Now, that was done. Okay, I'll show you also a function that I wrote. Maybe I should do it. Yeah, let me do it now. Let me try to find it. Hold on. Okay. One sample t interval for me. One sample t interval for me. One sample t interval for me. Stats inputted. We have all of that, right? All right. All right, let me use this function, see if it works. All right, let's go back here. And let's go here, paste this in. So in order to call the function, I take the function and then just put in my values. So I can put them in like manually, so like 30, and then x bar was negative 0.93 something. I don't even know, man. Or we could just, do the same thing we did above. So we could just do, let's do n. Interesting. Hold on. We do have variables. Let me try something real quick. So n, and then we have xdiff, and then we have, well, I didn't set them equal to variables. Let me set them equal to variables. So what do we need? We have n, we have x bar, which is my xdiff, my sx, and my mu. Mu is 0, standard deviation is that. Xdiff is data with the diff, dot mean, and then n is literally 30, or the length of data diff, yeah, okay, run those. And then we could say SX. Hopefully this works. Hold on. Because SX, I don't know if I put the variables inside. Oh my God, this gave me an interval. Oh. Oh, this is so funny actually. This is when I was using Python to answer my Khan Academy questions. I just wrote my own function because I was so sick and tired of doing the same calculations like over and over again because my teacher assigned Khan Academy things, and so I just made my own function and then I just put in those things that Khan Academy gave me like in the problem, and it would just give me the question the inputted values because there were different questions like, oh, they would ask you one for the answer and then they would ask you one with just the formula with the numbers plugged in, right? So that's why I guess I said inputted. So well, yeah, this is what we have basically, right? So you see t-test over here, negative 0 point whatever minus 0, we have that over here, 48 over here, divided by the square root of 30 over here. So yeah, I just need the one that actually solves it just to show you. Um, right over here. I think this one's it. That's my bad. I didn't look at the thing. Anyway, yeah. So let me just take these and put them over here and maybe run these again. There we go. And it rounds to how many? I told it how many? Let's do 4. There we go. So yeah, just like we had it, right? So negative 0.1044. Now this code is always linked in the description box below if you ever want to copy and paste my functions. I generally do not care. Use it as you wish. Anyway, yeah, I used it a lot for Khan Academy. Anyway, yeah, that's our T-stat. And so now you might be asking, what do we do with this T-stat? Well, good question. You obtain the p-value using the T-stat. So that's our O part. So what do I mean by obtain p-value? What's the p-value, you may ask? Well, the p-value is your probability value. An interpretation of the p-value is that assuming that the null hypothesis is true, there is a blank percent probability that we'll get a sample as extreme as we did for the mu difference. I'll explain it a bit also. Wait, is it the null hypothesis or the alternative hypothesis? Did I mess up? Okay, okay. I think I had it in my notes, right? I had it somewhere. Um, assuming. Ugh, why doesn't it let me do that? Okay, let me go to my phone because I can search it up on my phone in the GoodNotes app. So hold on. Statistics, search, assume that one second. Assuming that the null hypothesis is true. Where am I again? Assuming each other is a probability of the sample getting something other than 60. Oh, it's page 64. Let's look at page 64. So just to note, this was on page 30. Now let's go to page 64. Right here. So at the bottom, it says the interpretation of the p-value. So assuming that the null hypothesis is true, right? Okay, there is a probability between, wait, does that make sense? Oh, that's when I used the t table. But this was yeah. Well, okay. I didn't talk about the t table, but there is another way of calculating this with using the t table. But the essence is that there's a probability between blah 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 of getting a sample mean of something other than your sample statistic. Okay, anyway, that's it. Just wanted to make sure I was no hypotheses that I was working with. So anyway, where's my pen? Oh, here it is. Okay. So, why did I do that? Okay, so obtaining the p-value. Now, you might be asking, what is the formula for this? And I'll tell you in 1 second. I'm so sick right now. Okay. So for P, you either use a table, which is right the T table, but I'm not even gonna get into that. I hate the table so bad. I don't hate the table, I just like using the table. Sorry for my vocabulary. Okay, why is my pen not showing up? Okay, we're gonna have to close this again and open it again. Um, okay, so either we do that or we use TCDF, right, in our calculators, which you only have if you have a TI-84. If you have a TI-83, then you're just like me and you have to find another way to figure out to do your homework, basically. I had to literally write my own function for it. I took, oh my God, I stopped because I was so frustrated. I took weeks, literally weeks to find the function that does this for me. Or like the method or like the library, right? And then I finally found it. So yeah, all because I didn't have a TI-84 and I couldn't do my homework without using this function. I just couldn't find the p-value. All right. So let me, why can't I see it? I think my thing is frozen. Hello. Is my pen broken? Are you kidding? All right, so my pen is not working anymore. That's great. 1 second. Are you kidding me? I think my pen is not working. What happened? Oh my God. I think my pen literally just stopped working. Oh, great. Okay, so I'm gonna pause this and then I'll be back. All right, so the funniest thing just happened. Turns out all I had to do was unplug the thing. I genuinely thought this thing was broken. Are you kidding me? Literally, one problem ends and then there's another. Okay, we love this. Isn't this great? Now there's no internet. Okay, now I'll be back again and wait for the internet to show up. All right, so I'm back, or I guess the internet's back. So where was I? Okay, so to this. So obtaining the p-value. So to get the p-value, I'll explain it once we get it. You want to use a T-stat. So in your calculator, in your TI-84, let me go here. Oops. Your TI-84, you get your TCDF function, and then you put in, let me think. If this is a one sample T-test, you put in your lower bound, your upper bound, and then your degree of freedom. So let me think. Let me think. Um, when have I ever used? Oh, I'm tired. Okay, TCDF. There we go. But then that doesn't make sense because um a two-tailed test would be, oh, you multiply times 2 in these. Okay, makes sense. If it's negative, then it's negative. If it's positive, it's positive. Let me see something. 2 times the area, right, between that, 2 times the p-value if I use TCDF. Degree of freedom. Don't mind me, just looking at my notes, trying to figure something out. Be here. What is this? This is a 2 sample t interval. No, I don't need intervals. I need tests. I've done it here before. Hold on. Okay. So this is a function that I have because I never had a TI-84. So I had to figure out a way to do my homework. And where did it go? I'll do the Python way first, and then I'll see if I could do the TCDF way. 1 sample t. What the? Where's my stuff? I am so lost right now. Where's my stuff? Okay, I think it's this one. So I'm just gonna copy this. And what is going on? 1 second, this thing is frozen. Let me go here. All right, I'm posting it here. I mean, pasting it. Okay, and then for this, I'll just insert my values. So n was 30, mu was 0. What the heck went on right now? Parentheses. What is going on? Control Z. Okay, Control Z, Control Z, Control Z. Go back to what we had. Okay, so let's see. So my t, I'm just gonna set it equal to whatever. Oh, 1 second. Okay. What was it gonna do again? Okay, this. You know what I'm gonna do? Return. When did I round it? Oh, over here. So let's not round it. What is going on? I'm literally not pressing anything. Let's delete that round so that I could actually get the value. Oh, what now? Oh my God. When did that even? What is going on? X bar. Why is this happening? Am I missing something? Oh, you're kidding. Like, why? Why is this happening? Like, my keyboard doesn't want to work. Okay. X bar return. Oops. Okay, and then I'll set that equal to my t stat. Okay. So I'll run that, set that equal to my t stat, and then just put in 30 for my n, 0 for my mu, and then my t stat. You're kidding me. For my t, right? And then run that, and then what now? When did I even write this? Oh no! It's okay, I can rewrite it again. If type test equals yes, inset that. Let me see. Should be here. This one should be indented. This one should be. I'm so confused. Is it because I didn't put. I'm literally so lost. Like, what did I do? If type test is equal to yes, p-value is area times 2, right? Is a two-tailed test, that makes sense, right? Okay, we should do that. And then do this. And then do that. Oh, okay. Elif type test is no. If t is blah blah blah, then indent this. Elif t is greater than 0, then do that. Okay. What now? So non-times int t df and what? Um, what? What does it even mean? Uh, like that. That's Tstar SF statistic df equals 1. What do you mean? Okay, string. Oh, it's because it doesn't take float. Oh no. Doesn't take integer. But it is a float though. Is this better? Oh my god, why? It is a type of thing. Do we set it equal to float Ttest? What? Tstat. Oh, I'm done. I set Tstat to this entire thing. I don't need that. I need Tstat to literally just be this number. So, I'm gonna modify this function real quick. Let me delete this. Go back here, go here, delete that, copy this whole thing, paste it in here, and just remove the print statement and just say return t statistic there. And then I can set that equal to my t stat. And then I can run this. And then I could say, is it a two-tailed test? Yes. And then it's going to give me my p-value. Great. That's amazing. Okay. Took long enough. Anyway, now let me explain to you what I just did. So, where is my pen? Okay. First, let's start with the big question. How do I know if it's a two-tailed test, a right-tailed, left-tailed, whatever? So I have this image over here. So if it's a two-tailed test, it's going to be the first option, right? Where we have equal signs in our hypotheses. And now my pen is not showing up, so I have to close this again. Anyway, if it's a right-tailed test, it's when you have a greater than equal sign in your alternative hypotheses, and left-tailed is when it's less, okay? So two-tailed is when you have equal signs for both, which I'll show you a visualization. I think I had it over here saved. Right, so this is what a two-tailed test looks like visually. So you have your normal distribution, right, because we check for normality, so our data is normal. And then what we're basically doing is we're trying to find the probability of the mean difference not being equal to 0. And so whatever that basically we're just trying to find it, how do I say, not equal to 0, but the t-stat, the test statistic would be the thing in red, and we're just trying to find the probability that it's greater than, like, anything after it and anything, like, how do I say this? Okay, give me 1 second. I'll think about how to say this nicely. So it is a two-tailed test, and so Let me think. Your lower bound in this case would be negative 0.1044. It would be infinity. No. Lower bound, that would be your upper bound because it's negative. Let me think. Negative infinity, which is 1e99, upper bound, negative 0.1044. Degree of freedom would be 30 minus 1 because the degree of freedom is equal to n minus 1, which is 30 minus 1, which is 29. So 29, and then you would use TCDF on your TI-84, and then it would give you that answer, and then you would multiply this by 2 if it's a two-tailed test, which it is, and it's a two-tailed test because we have a not equal sign. So I think that's what it is. Don't quote me on that just yet. Um, Let me try something. So I have my little thing here. So my t, right, was 3.18. So in this case, in that example, over here though, it was negative 0.1044. And then here, it would be 0.1044 because you disregard the negative, right? Because it's the same. That's another question. Why do we disregard the negative? That would be something to look into. I cannot explain that right now. I just know it by heart that you disregard the negative. Because at this point, you're trying to find this area here. Oh, right, because hold on. So the test statistic is this value. So we're trying to find the area. What we just found was this area here by doing this. That's this p-value. Well, not really. That's just, well, one p-value. I guess we could call it p-value, but it's not just yet. That would be if it was a left-tailed, is it? Left-tailed, because we're trying to look for the left. And this would be a right-tailed. And then not equal to would be the probability of both of these combined, because this stuff inside is when the Ttest. Interesting. 1.57 was what? 1.57 was, oh, it was 1.57. Oh, it was the mean difference. Right, that makes sense because it's in the middle. Okay, I'm just gonna try to walk through this. I haven't done this in a little while, so let me think. So I have this. That is not a straight line. Okay, then I have my normal distribution. This is what my data looks like, theoretically, at least. All right, the mean we know in a normal distribution is always in the middle. So then we know that the mean is negative 0.93133 or something. Um, Let me check something. So 1 second. 1, 2, 3. Okay. Oh, my audio just went off. All right, where were we? Oh my God, I want to be done with this. All of this is fun. It's fun. Okay, anyway, okay. So my mean is that, right? And then my test statistic is what we got, and so that's somewhere around here. And that is negative 0.1044. And then we would look at it here positively. And then the area that we're trying to find, because it's a two-tailed test, is this area here. So I'm just trying to understand how this is working out right now. I'm just trying to see if I have an explanation. Don't tell me it was inverse T instead of TCDF. Second bar 6. P-value. Lower, upper. Oh, because it was positive. Because the T statistic was positive. Okay, yeah, so I think I'm right. Because the T statistic was positive in this case, it was 3.18, we did 1E99, right? Because that was the interval, and then the DF, right? And then we multiplied it by 2, and then it gave us that. But if it's negative, in my case, in our case, it's negative 0.1044, we would make it our upper, and our lower would be negative infinity, and then we would just multiply that times 2 to get the other side. Because I'm trying to see, so, oh, but that's a t-test instead of a t-CDF. Well, yeah, there's two different ways. You could do a t-test or a t-CDF. I'm just trying to figure out. Let's see. I know I wrote it down somewhere. Let me see real quick. Oh, would you look at, literally tell me how. Tell me how I just end up on this page. This is crazy. Okay, so suppose the conditions are met to test the hypotheses, compute the standardized test statistic, find the p-value by calculating the probability of getting a t-statistic this large or larger in the direction specified by the alternative hypotheses in t-distribution with degree of freedom equals to n minus 1. That makes sense. Okay, so it's the probability, the p-value is a probability of getting, oh my god, didn't I read that before? Yeah, so the p-value is the probability of getting that t-statistic or more extreme in a sample, assuming that the alternative hypothesis, not, sorry, assuming that the null hypothesis is true. Null or alternative? I don't even know at this point, whatever. Let me think. No, was it null or alternative? Again, here we go, me forgetting. This is page 64. 77, 64. What was it? Assuming that HO is the null hypothesis. Okay. Assuming that the null hypothesis is true. Where was I? Oh, here. Okay, so the p-value by calculating the probability of getting a t-statistic this large or larger in the direction specified by the alternative hypotheses in this t-distribution if df is equal to n minus 1, which makes sense. So our p-value is option 3, right? So we're taking, here you go. See, I literally knew this. Okay, hold on. See, I was like, yes. So you can see the negative t and the positive t. So that's why. So it's like the t-stat, you want to treat it as like two possible options. Because, well, when you have a two-tailed test, because you're trying to figure out the probability that you're getting this value, even if it's negative or positive, right? So in this case, we're trying to say that it's not equal to mu to the original hypotheses, which is 0. Interesting. So if the mean is up, I'm just thinking out loud. 1 second. Okay, so our t statistic is like 0.1044. And then we're looking at the probability of getting this test statistic or larger. Oh, okay, yes. Okay, it makes sense, right? So we're looking at getting that test statistic exactly or larger. That's why it keeps going. So let me just go back to my whiteboard. Okay, now I can explain. Okay. See, like I always have my notes. This is good. All right. So this is my test statistic. This is my test statistic, right? So the p-value is basically trying to find the probability of this test statistic happening, right? Or larger. So this statistic, wow, this test statistic happens at this exact point. Like let's say, well, let's call it t, obviously. And it also happens at this exact point, right? Besides the negative, right? So we want to know the probability of it happening at this exact point and then larger. So that includes this area over here and this area over here, right? And then this area in the middle is the probability of that test statistic never happening, right? Or like appearing in that sample. So we want that test statistic. Hold on. Wait. Because if our alternative hypothesis is that mu difference is not equal to 0, and we have a test statistic, oops, well, our t stat of 0.144, our test statistic, what is the interpretation of a test statistic? Because there's always an interpretation of the p-value, but what about the test statistic? The agreement between your calculated test statistic and the predicted values is described by the p-value. The smaller the p-value, the less likely your test statistic is to have occurred under the null hypotheses of the statistical test, right? Okay, but the test statistic, what does it mean? Like, what's the definition? A test statistic is a statistical test that is used to compare the means of two groups. It is often used in hypothesis testing to determine whether a process or treatment actually has an effect on the population of interest or whether two groups are different from one another. Right? No. The t-value is a way to quantify the difference between the population means, and the p-value is the probability of obtaining a t-value with an absolute value at least as, okay, this makes sense. Okay, right, because essentially, I think that, I don't think I was ever taught specifically what the t-test is. I just learned how to use it with p-value. For each test, the t-value or the t-stat is a way to quantify the difference between the population means, and the p-value is the probability of obtaining a t-value with an absolute value. Okay, so I'm assuming that this is, I think, so we could say, is this the true, is this, wait. Is this the true mean difference? Is this what we're looking at here? And then we're just trying to figure out with the p-value if that t-value is statistically significant, right? By trying to figure out the probability of it occurring during this process of normal distribution. Is that what's happening? Oh wow, okay. Let me see. Oh, let me just screenshot that just in case. Okay. The largest and most restrictive sample of general hypotheses is actually true. A negative t-value only means there is a significant decrease between the former set with the next set. So does that mean, well, I do have a negative, right? So I'm assuming, right, treatment 1, treatment 2, and then if this is negative overall t-stat, then that means that there was a significant decrease in distance. So I know that this was a 45-degree angle, this was a 60-degree angle. So the essential idea is that a 60-degree angle, if the catapult was placed on a 60-degree angle, then there was a decrease in distance. So 45-degree angle is better because 60-degree angle went less distance. That's not English, but okay. But we're trying to see if that's statistically significant. Like, is that enough? Do we have convincing evidence? Like, yeah, we have that, but like, do we have convincing evidence? That's how we check. Let me see. No, not this. The p-value is the probability of the test statistic being at least as extreme as the one observed, given that the null hypothesis is true. So then what is the test statistic? Is it the statistic for the test? It's called that for a reason. Oh, wait, no, let's go to the second link. Whoops. Okay, so we'll do AP statistics for interpretation templates. All right. Okay, where is the test statistic? All right. Test. But I don't want the p-value. We always interpret the p-value, but what about the test statistic? Huh. No. A test of significance is a formal procedure for comparing observed data with a claim, also called a hypothesis, the truth of which is being assessed. Oh my god, okay. The claim is a statement about a parameter, like the population proportion p or the population mean mu. The results of significance tests are expressed in terms of probability that measures how well the data and the claim agree. Okay, sure. All right, so example, if the sample mean significantly different than the population mean, is the mu difference significantly different than the population mean difference? In order to determine if two numbers are significantly different, a statistical test must be conducted to provide evidence. Researchers cannot rely on suggestive interpretations. Okay. We did that. We did that. Here we go. I don't want the z-score, I want the t. P-value. Where's the t-star? You're kidding me. Do they only join with the z? Okay, well, it doesn't matter. Tell me what it means then. Okay. Oh, I guess they use it because they know the standard deviation. Sigma. I don't even know this one. Okay. Uh, is simply the z-score for the sample mean. The only difference is that the population standard deviation is divided by the square root of capital N, just like when a confidence interval is computed. To complete the test, the population standard deviation must be known for the variable, blah, blah, blah. Okay, but can someone tell me what it means? Like, the probability of obtaining this score when the null hypothesis is true. So when, in our case, when the mu difference is equal to 0, meaning that there is no difference, huh? That doesn't make sense. What is the probability that we get that t-stat? Interesting. Area to the right of z, or in this case t. Area below the curve, area left. The probability of obtaining scores. So area to the left of z is the probability of obtaining scores lower than z. Area to the right of z is the probability of obtaining scores higher than z. So in this case, when we have area to the right of z, left of z, or in this case, or t, it's the probability of obtaining scores not equal. I'm so confused. The p-value greater. P-value represents the probability. I can't breathe. Um, huh. Oh, here we go. Yes, yes, this is what I wanted. Okay, a two-sided alternative hypothesis is used when there is no reason to believe that the sample mean can only be higher or lower than a given value. Researchers are only hypothesizing that the values are significantly different. In the example, the alternative hypothesis was one-sided, so it was only necessary to look at the probability that the sample mean was larger than 100. However, when the alternative hypothesis is two-sided, which means that the alternative hypothesis is not equal to whatever value we set it to, the sample mean can be higher or lower than that given value. So researchers must look for both extremely high and extremely low values. This means that alpha is located at both ends of the curves. Half of alpha, alpha, by the way, is 1 minus the confidence level, which is, in this case, wait, but that's confident, wait, what the heck? Oh my god, whatever. Therefore, in two-sided cases, the p-value is obtained by multiplying the area to the right of z by 2. Okay. Only after doubling this value, the p-value can be equal to alpha. What? I'm just not understanding. The area to the right of z was blah blah blah. So if the alternative hypotheses were two-sided, the p-value would be that. So something greater than that. So that's the probability of having a test statistic of that size or larger. Anything different? No. I mean, yes, but also no. Like, I need more information. Um, let's see. No, no. Oh, Jesus Christ. This is a standard deviation. No. In formula, blah, blah, blah. What the heck? No, I am not answering the test question. I want to know how about being tested. Random variable that is counted, blah, blah, blah. You can use it to determine. A test statistic is a random variable that is calculated from sample data and used in a hypothesis test. You can use test statistics to determine whether to reject the null hypotheses. The test statistic compares your data with what is expected under the null hypotheses. The test statistic is used to calculate the p-value. A test statistic measures the degree of agreement between a sample of data and the null hypotheses. Okay, I think the answer's in that sentence. I just have to really understand that sentence. Okay, so what do they mean by degree of agreement between a sample of data and the null hypotheses? So if my null hypothesis is the fact that my mu or my mean or my average difference in distance traveled by those gummy bears is 0, meaning that there is no difference, then if that's the null hypothesis, right? I'm trying to prove that there is a difference. So that's why my alternative hypothesis is that UDIF, or the average difference in distance traveled by gummy bears, is not equal to 0, meaning that there could be a negative or a positive difference. So my t-stat, which is negative 0.44, no, 1044, measures the degree of agreement between my sample data and the null hypotheses. So how much they agree. Okay, so its observed value changes randomly from one random sample to a different sample. A test statistic contains information about the data that is relevant for deciding whether to reject the null hypotheses. The sampling distribution of the test statistic under the null hypotheses is called the null distribution. What? The sampling distribution. Sure. Okay, when the data shows strong evidence against the assumptions in the null hypotheses, the magnitude, what is this, physics? No, I'm not using that word ever again. Magnitude, oh my god, of the test statistic becomes too large, blah, blah, blah. The test statistic for a z-test is the z-statistic, which has a standard normal distribution under the null hypotheses. Suppose you perform a two-tailed z-test with the alpha level of 0.05 and obtain a z-statistic, also called a z-value or a z-score, based on your data of 2.5. This z-value corresponds to a p-value of blah, 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 blah. Okay, no. Okay, I understand how to get the p-value, but what is it between itself? Like, what in the world is it? Like, there is no, it just says a test statistic measures the degree of agreement between a sample of data and null hypotheses. What does it mean? Like, what does that mean? Like, I understand that we use it for a p-value, and then I definitely understand how to interpret the p-value, but what is a test statistic? Like what? Okay, let's think. Oh my god. I want some shrimp scampi right now. Okay, vamos a pensar. Vamos a pensar. I mean, I like this. What does it mean? Why are we using p-value? Okay, a significant test of proportions. No, I don't want multiple choice. What does this even mean? No. Maybe there's answers in the images. We reject HO, reject HO. So this inside is what? Right, because a t-test is what we got given all that data, and so to get larger than that, then we reject the hypotheses, but anything inside is basically not having that t-test. So therefore, we don't have enough evidence to reject the hypotheses, and we actually have enough evidence to not vote for the alternative hypotheses. Rejection region. Acceptance region. This is what I wanted. Okay. So apparently let me save this. Right, so I basically told you the opposite. It's literally the opposite. So in this case, um, let me lock this. So my T-stat, right, over here, um, is 0, negative 0.1044. And then over here is 0.1044. And essentially, um, ignoring these like values here, I'm looking for the rejection region. So if I multiply this by 2, right? But that's not the p-value though. I have to find the probability value of this occurring, and I have to find the probability value of this occurring, right? Which would make sense. The cumulative, I would get the cumulative distribution or density of each point here, but it's the TCDF, the cumulative distribution function, right? Makes sense because you're getting each t value and you're getting the cumulative probability of each t value happening up until this t value. And that's what it means when it's extreme or larger. So to find the probability of that, we would do TCDF and we would do negative 1e99, blah, blah, blah. And then what did we say we got? Well, that only gave us the p-value multiplied by 2. But I just need this really quick. So let me take this. T-stat area. So let me just use T-stat and then here put 29. And let's not round it. Maybe I shouldn't round here either. It could affect my answer. Yeah. Right, and so if I multiply this by 2, it's the same answer, right, that I got in my function. Okay, so essentially, I'm going to put decimal places, so 0.5412. So this is 0.5412. The area here is 0.5412. And then that means that over here, 0.5412. And so we take that 0.5412, because that's, well, and then we multiply it by 2, and we get 1.08 something, and that is our p-value. Right. So we get 1.0824. Okay, so we get 1.0824, and that's our p-value, but I'm just trying to figure out, let me think. So 0.5412 is the area here, the cumulative density of this occurring and like until negative infinity. And same thing with this. And so the p-value is 2 times that because it's a two-tailed test. And so that means, what does that mean? It means that our test statistic is that, and we're trying to find the area of our test statistic being that. So I'm assuming, wait, so it supports the null hypothesis? Because this is the rejection region for the null. And so having our t-test, anything, nah, I don't even know what I'm saying at this point. Okay, let's move on to the interpretation. So the M part is make the conclusion. So p-value. So if our p-value, so we have our alpha. So alpha, by the way, is always 0.05 unless stated otherwise. So alpha is 1 minus your confidence level. So essentially this is a 95%. I believe, right? Because 1 minus 0.95. Hopefully it's 0.05, something like that, right? Okay, and then, yeah, that's our alpha. And so if our p-value, well, our p-value is 1.0824, and we have to determine, well, obviously that is very much greater. So because our p-value is greater than alpha, we fail. That's so ugly. We fail to reject the null hypotheses and do not have convincing evidence that evidence of the alternative hypotheses, which is that let me think. What was it again? That the mean or the average distance, difference, the average difference in distance traveled, this is so sloppy, traveled by gummy bears in each treatment. Or no, hold on. Not there is no difference, that there is a difference. Because, okay, hold on. That there is a difference in the average. That doesn't make sense. Does this make sense to you? That there is a difference in the average difference? Or that there is a difference in the average difference in distance traveled by gummy bears in both treatments? Question mark. Right. So the answer is, for now, it is true that it's not true. We just fail to reject HO, and HO is that there is no difference. There's no difference. So we do not have convincing evidence that there is a difference, is basically what our conclusion is. So we use 2 times the probability of that test statistic occurring, and we compared it to the significance level. So it's obviously not statistically significant. Yeah. Okay. Oh, 1 second. Someone's calling me. I'm just trying to really understand the Ttest test. Like, how do we, why? Why is it that we use a Ttest test for a p-value? Like, what's the reason? What's the reason? Like, I know how to do this. Like, I just don't understand why I'm doing this. I just do it though. Not the whole process. I'm just talking about using the Ttest test. Like, that's the only thing that I'm not really understanding why. Like, what's the reasoning behind that? The T-test is this, right? And so we're taking, like, visually, right? We're taking the red parts, which is the probability of having that T-test or larger or extreme, No, not really. Actually, yes. We're adding them together because times two, right? And but why does it call it the rejection region? Um, why? I just want to go to sleep. I'm so tired and sick. Um, I literally do this to myself because I could have stopped like 2 hours ago, but it's okay. It's okay. Um, I literally forgot what I was gonna say. Oh my God. Okay, yeah, I remember. So yeah, what's the point? Literally, what's the point of a t-test? Okay, so we take the t-test, right? And we calculate that. And if it's the probability of that t-test happening, something about the agreement between the data and the null hypotheses. So essentially, the null hypotheses we reject if it's extreme or larger, question mark? Nah. Okay, so we take the t-test and it's the p-values of, we take the probability of it happening, or we take the probability of that value, of a value larger or of a value like that or more extreme happening. And whatever the probability is, if it's greater than the significance level, then it is not statistically significant. Therefore, we do not have enough evidence for HA, and we fail to reject HO, right? Because it's greater than the significance level. So it has to be less than the significance level. That probability of T happening. Okay, who invented the significance level? Like, yo, like these things, is this real? Is this even real? Like, literally. Okay. Um, it is way too large though. So 1.0824. That's the probability of this t-test happening larger, or like a t-test such as that happening, or larger, such a, okay, this is the, okay, I can't speak. 1.0824 is the probability of getting a t-test such as the one we just got, or larger or more extreme, in another sample. And because it's greater than 0.05, we do not have. So we're saying that this could have happened purely just by chance. Okay, we're saying that this could happen purely by chance because it's greater than 0.05, greater than the significance level. It could have just happened by chance, so it's not statistically significant, like it's not significant, right? That's what we're trying to say. But where does a t-test, okay. But like, if I just had the t-test, what could conclusions, what is that? Is that the actual true, it's not, I know it's not the actual true mean difference of distance traveled by gummy bears, but what is it? Like, essentially, what is it? Huh. Anyway, I got my answer. We'll research this some other day. It's a question that I have. I've always had this question, like literally. Um, Maybe I'll ask my stat teacher on, what day is it today? Saturday. I'll ask her on probably Tuesday because I'm not going to school on Monday. Hopefully, I don't want to. So, um, it depends. Wait, what's due on Monday? What's Monday? Oh yeah, I have this due on Monday. It's fine. Um, Okay, all right. So what was I gonna say again? I don't know. Oh yeah, so I used this function, right? It gave me my p-value. Um, oh, I forgot. You could also use a t-test on your calculator instead of using TCDS. When you use a t-test, you don't have to multiply by 2. Um, okay, so when you use a t-test, you want to go to, I have it in my notes. I had it here, right? You go to, one second, I know it's 6. Um, didn't I have it? Oh, this is to get Tstar. This is for confidence intervals. We don't need that. Um,
What the heck? Okay, here we go. Here we go. What? Here we go. Like, why can't I speak, honestly? Ugh. I'm so tired. Okay, where is the function? Not the function. I mean, yeah, the function. Yes, that's what it is. Where am I right now? Oh my god, is this it? Oh, never mind. I literally took a step-by-step picture. One more stat. No, that's not it. Okay, I'm trying to find that. Where in the world was it? I had it before. Oh my god, is this it? The area when it's not 64. Oh, when it's not 0. So this is the area when it's not 0 in my case. And so this is the area when it's also not 0. Oh, you're joking, right? Literally. Okay, so back to the question. Apparently, it means rejection region of HO rejection region. So this red section right here is the area of HO not being equal to 0. Not HO, but about our mu difference not being equal to 0. Wait, no. Of being equal to 0, because this is our HO. So we're rejecting the idea that it is equal to 0. So, and if the probability, wait. Okay, we're getting somewhere here. I'm trying to think. This area is when HO is equal to 0. So the 0.5412 together is the probability of HO. Oh. So 0.5412 is the probability of HO being rejected. And because that probability was greater than the significance level, we fail to reject HO and do not have convincing evidence for HA. But let's say the probability was very much less than that, and it was actually like something like 0.1023 or something. That's the probability. It's still the probability of HO getting rejected or being rejected. So, but because it's less than alpha, this p-value p-value because it's less than alpha. In this case, we do reject, right? What happened? We reject HO and do have convincing. I promise that in real life I really do write nicely. It's just that I don't have the time sometimes, to write nicely. For HA. So convincing evidence for HA, okay. So essentially, the probability of HO being rejected. Oh, I can't think. That's the probability of HO being rejected, right? So we're trying to find at all times the probability of HO being rejected, but we're trying to see, okay, not really. The probability of HO being rejected would be then what the heck does a T-stat have to do with, okay, it sets the interval in which HO can be rejected. The T-stat sets the interval in which HO can be rejected, right? Because after the T-stat, anything larger or extreme on the basis of the T-stat would be considered a rejection area or rejection region for the null hypothesis, which is HO. I'm trying to think. Okay, and then I don't know, this is all theory right now. This is just my thought process, like the answer we already got. But I'm just trying to think. I'm trying to really think right now. Like, what in the world am I doing? Like, why? What's the why in this? Someone needs to explain it to me. Because girl does not understand. Why T? Like, why T? Like, what? Okay, so I'm assuming the T, right, the T statistic, determines the interval in which HO can be rejected. And then we take the probability of that interval happening, of the HO rejection region. So the probability of HO being rejected, the probability of HO being rejected, and maybe that's what it means in that article when it said it's the agreement between the sample data and the null hypotheses. That's test statistic right there. So the probability of the null hypothesis, which is HO, being rejected, and then if that probability, right, that p-value is greater than alpha, then we fail to reject HO because it's not statistically significant. But if it's less than alpha, we do reject. So we reject HO. Here we fail to reject. Oh, what the heck? HO. So the probability of HO being rejected. Is that what the p-value is? The probability of HO being rejected is greater than... That doesn't make sense. What? Is greater than alpha, then we fail to reject HO? But if the probability of HO being rejected is less than the significance level, then we do reject HO? That doesn't make sense. Maybe this is the part that doesn't make sense. The probability of HO being rejected. But no, I think that's the T-stat. No, the T-stat establishes the probability. Maybe not the probability, but the interval in which HO can be rejected. And then within that interval, we find the probability or the cumulative density of each of those points within the interval, and that gives us the probability of that entire area in which HO can be rejected, right? And so it would make sense that the probability would be the cumulative density together, right, would be the probability of HO being rejected. I don't even know. I don't know what I'm saying. I'm just trying to think right now. I don't even know. I need a break. I've been at this for hours. And I wanted to paint today. Could you believe that? It's already 7 p.m. I don't think I have time. Yeah, I don't. Probability of HO being rejected. Well, now I know that T-stat, okay, I think we could define that T-stat sets the interval in which, for the rejection region of the null hypotheses. But then what about the acceptance region? Do we ever look at that? What if we want the acceptance region? So would the alpha value switch if we take the acceptance region, the probability of HO being accepted? Because essentially we're always looking for the alternative hypothesis to be true. So we're trying to look for the probability of rejecting HO, and so we're trying to look for the fact that that probability is less than alpha, that it's statistically significant. But p-value is assuming that HO is, what the heck? The interpretation of the p-value, okay, this might be counterintuitive, because it's assuming that HO is true, the probability of getting a value as extreme or larger than our T-stat, which is what, 0.1044, is what? Is 0.5412. Is that what it is? Assuming that HO is true, the probability of getting a value as extreme or larger than 0.44 in a sample is 0.5412, purely by chance. Interesting. Assuming that HO is true. Oh, that makes sense. Wait, didn't I write that? I knew I said that somewhere. Purely by chance. And that's because, okay, assuming that HO is true, we could get that value, but it could be purely by chance. Oh, okay, so this is the probability. Oh, but if HO is not true, then we didn't get that purely by chance, and instead it was statistically significant. No, but that doesn't make sense, because we always say, actually no, that does make sense. Okay, hold on, let me think about this. Okay, I have to stand up for this. I'm trying to think. I am so close to the answer right now. I'm so close to understanding. Like, I just have it all in my head. God, assuming that HO is true. So, if HO is true, right, the probability of getting a value or extreme, a value as extreme or larger than our test statistic is that probability, is that rejection region. So what is this? This is our rejection region, is it not? The probability of, wait, here is the probability of HO rejection, because that's a rejection region. Oh wait, that's not it. It's 1.08. Oh my god, I'm so sorry. I forgot. Oh my god. Did I do that? Whoops. It's 1.08. I've been doing this wrong. Okay, hold on. Let me just fix that. It's 1.08 something. Okay? So that's the probability of HO rejection. But because HO is true, we're saying that this could have just happened purely by chance. But because it wouldn't make sense. I don't know. Assuming HO is true, the probability of getting a value as extreme or larger than the test statistic is 1.08. In a sample, purely by chance. Right, just because it happened by chance. But if it's false, the probability value blah blah blah, is it purely by chance? No, right? What's the alternative definition? Get it? Haha, alternative hypotheses. Okay. The probability of getting a value as extreme or larger than that test statistic is 1.08. But 1.08 is the probability of HO, of rejecting HO, meaning that why would it, okay, assuming that the null hypothesis is true, right? Why would the probability of getting a value, so assuming that there is no difference in the distance traveled by gummy bears, the probability of getting a value as extreme or larger than 0.1054 for the average difference in distance traveled by gummy bears is 1.08. It's like literally 100%. It's more than 100%. Let me think. Is getting a value such as that is 100%. 100%. Purely by chance, though, in a sample, but that's the probability of HO rejection. So what does HO rejection and HO being true have to do with each other? They're opposites. HO is true. HO is true, but what the heck? HO is true. Sorry, I'm taking a quick drawing break right now. I literally cannot think. This is very disproportional right now. We're gonna pretend she has an eye patch. This is horrific. Anyway, as I was saying, assuming the null hypothesis is true, but then the probability of the t-statistic happening is like 100%, but that probability is the probability of HO rejection. Okay, I'm not gonna do this anymore. I'm gonna go. Okay, this is a question for another day. We're gonna move on to the one thing I wanted to mention was we want to find the area when H, whatever that is not equal to 64. Yeah, whatever, bro. I don't understand. So, I don't know. I just feel like the answer is right at the tip of my tongue. Whatever. Anyway, another way to do this is by using t-statistic, your t-test in your calculator. That way you don't have to multiply by 2. You just put your lower bound, your upper bound, and then I don't even know at this point. Just do whatever. Just Google it. I just don't know. Hold on. I'm just so frustrated with the fact that I can't explain like t-test. So that's the probability. This is the probability of HO not being not being equal to 0, or of UDiff not being equal to 0. UDiff not being equal to 0. That's so ugly. That looks like a 6. Okay, not being equal to 0. This is our alternative hypothesis, that there is a difference. So this is the probability of rejecting HO, but having evidence for HA, not accepting, right? I'm sorry. No. Yeah. Rejecting HO, but having evidence for HA, or failing to reject HA. Evidence for HA. There's evidence for HA. Let me think. So that's the probability of finding evidence for HA. Maybe that's a different perspective, right? So we had, that looks so ugly, our distribution, and we had our t-stat like here, right? And so this over here is the probability of finding evidence for HA. So when we take that that area, when we find that probability of T being greater than or larger or as extreme, that probability, right, is finding evidence for HA. And if that probability is greater than, then we fail to reject HO and do not have evidence or convincing evidence for HA. It's another different perspective to look at it, not of like a rejection region for HO, but like just finding evidence for HA. We want to find the area when HO is not equal to 0. When HO is not equal to 0, but that's HA. Excuse me, not HO, UDiff, right? But that's HA. What was I saying again? I forgot. Okay. Right, so evidence for HA, if that's greater than the significance level, so if it's not statistically significant, right, all of this evidence, if it's greater than the alpha level, it's not statistically significant, and therefore we fail to reject. So it's like useless. We're saying it's useless. But essentially this provides all the evidence that we need for HA. Okay, so I guess the probability, that p-value, is the evidence that we need for HA to prove it. that we do have convincing evidence for HA, but if it's not, but if it's greater than the significance level, then it's not useful. Okay, that's enough thinking for today. I am going to end this video here. I'm not even gonna bother putting this in my project doc. I'll do that tomorrow or some other day. I don't even know. Because girl has to eat food right now and do other things. So yeah, okay, so that was it for today. I'll put this link down below, and yep. Oh my god, ignore that. Okay, let me erase that because that is so ugly. Okay, let's just make sure that's gone. Alright, beautiful. Bye!